Hello. So we're going to continue with the direct detection theme. Today we are going to start focusing on some of the specific techniques other than scintillating crystals that we discussed at the end of last talk. Please, at any point, if you have any questions or things that you would like to say, just do it. Don't wait until the end. You can, yeah, we can discuss anything during the talk. Okay, so at the end of last talk, we discussed that we have a signal from DAMA, but that is a very contested signal, and that there is a huge effort to cross-check it. And so far, all the cross-checks have been negative. Also, that this possible signal, we don't know what it is, and when I say that we don't know what it is, we don't know if it is coming from electron recoils, which is mostly what happens when you have a gamma, a photon, a high energy photon, or a beta that is just an electron moving around, okay? That knocks one of the electrons in whatever target material we are considering. In the case of DAMA, we know that there are three different elements in the crystal itself: sodium, iodine, and a little bit of thallium. So the other possibility is that we are having nuclear recoils. This is what you would expect because of the cross-section that would happen between neutrons and WIMPs. For neutrons, the reason this dominates over this is that, well, here you have the possibility of the neutron to interact with the nucleus directly in a coherent way, or even in an incoherent way if the neutron has enough energy. And you've been discussing these different things over the different courses, why the low energy enhances the cross-section, so this is much more likely to happen. And also the neutron is neutral, so it cannot directly interact with electrons there, okay? So now, as I said before, we are going to focus on noble liquids. Noble liquids come in many different flavors, and we are going to discuss from a fundamental point of view why there are so many efforts using noble liquids to look for dark matter. There are two different types of approaches. The original one that was devised for looking for WIMPs, in which you are essentially looking at what I mentioned before, the scattering between the WIMP and the nucleus that then exchange some kinetic energy, and you are trying to see that. And now there is a new generation of experiments that are trying to extend the reach beyond the WIMP to lower masses. And in particular, even to dark matter candidates that interact with electrons instead of the nucleus. Okay, so we're going to focus here, and remember from last talk that we had some checklist that we produce for looking into which targets are good targets for looking for dark matter, and this is kind of our wish list of what we would like to have. Ideally, we would like to have nuclear recoil, electron recoil discrimination if we are looking for WIMPs or WIMP-like particles that interact with the nucleus because of all the things that we just discussed. Then we have this trade-off between heavy nuclei that have a large cross-section, but we want to have light nuclei in order to be able to have an efficient kinematic transfer, okay? And for this, well, we are going to focus on this. The noble liquids do cover all of these conditions, and also they kind of cover the conditions for the dark matter electron interactions when we are looking at low energies, okay? So why noble liquids, okay? So the reason is that many or all of these produce scintillation light. So you have a signal. So if you deposit energy into a noble liquid, it will produce light, which is not always the case with other elements, okay? And one thing that is key is that the light that is produced during scintillation has a wavelength that is not absorbed easily by the material after creation. This is also not very common, because when you have in a whatever material that scintillates, is that in many times the excitations are the same in which it's easy for the material to get excited even through photons or through through ionization interactions, okay? And that is not ideal because, well, you produce a photon, but then you absorb it right away. So then you are not able to see it coming outside of the material, or you see this after a long transport of the photon inside the thing, of being absorbed and re-emitted and other stuff. So in order to solve those problems in other materials, you need to add other components to the mixture in order to shift the wavelength, and that has, of course, a lower efficiency, and yeah, that's not great. So this is completely key. Then this also translates into a relatively low energy threshold. Why? Because if you have more photons, then this means that you need to deposit a smaller amount of energy to produce a large number of photons. So you have a low energy threshold, or a relatively low energy threshold. Then this is also very important, that you can build things that are very big, because you have a lot of these materials around. You can just purify them relatively easy. The chemical purification of noble gases or noble elements is easy, so you can produce that. And you can produce them extremely pure, okay? And then you have this self-shielding characteristics that is also very important, and it's very much exploded by the many experiments, in particular xenon, is that if you have a material that is very dense and you have position resolution to know where the interaction took place, well, you can just discard whatever happens close to the edges of the detector, and the material itself is shielding the inner core of whatever of your detector from outside radiation. And we will discuss that also in detail. Then this is also a key reason, and one of the reasons why it was selected in the first hand for many experiments, that you are able to tell apart nuclear recoils and electron recoils interaction. And as I said before, if you are looking for WIMPs, that's absolutely a game changer, because most of the background is produced by electron recoil interactions. Okay, and which is very, unexpected, is that there are two different techniques for doing this. One that is the pulse shape discrimination, that is the one that we are going to discuss first. And then the other one is exploiting the fact that the amount of light and amount of ionization that is produced in a noble liquid is different if you have a nuclear recoil or an electron recoil. And these two things happen at the same time. They are not, it's not a given, but yeah, this happens in noble liquids, okay? Well, so essentially, yeah, I'm going to move forward. And sorry, many of the slides at the beginning are boring, but we need to get to why we are using these things. So here is a list of many of the noble elements, okay, and their characteristics. So here, what is important to look at is essentially, well, remember our wish list from the beginning, that we want things that are heavy. So in that sense, we want xenon. Xenon has a lot of nucleons in the nucleus, okay? And also, it is very dense. So the self-shielding characteristic is good. You are able to produce detectors that are very massive and still fairly compact, okay? At the same time, there is the problem with with the efficiency of the kinematic transfer between dark matter and the target itself, okay? In that sense, there is also krypton, argon, and neon. So we are going to consider xenon, argon, and neon for the next discussion. That are the three elements that have been mostly used for many different reasons. And essentially, this is the way to select stuff, okay? So again, the star element here is xenon because of many reasons. The first one is that the scintillation light that it produces, it has a wavelength that can be directly seen by the cheapest and most common photon detectors that are photomultiplier tubes, okay? That is amazing because that simplifies the construction of your detector a lot. You don't need to do anything to the light that is produced, okay? You just need a PMT with a window that allows UV photons to go through. That's not the case for all the other elements. For all the other elements, the light that is produced, you need to do stuff. So you need to absorb it in a different material and then re-emit it at a different wavelength in order to be seen. And that is a problem, okay? Because this reduces the amount of light that you are ultimately going to get. And then this column is also absolutely critical. Xenon, again, here shines because it has no long-lived isotopes that are radioactive. So you purify it, and as long as you are able to chemically purify it and just have xenon there, you won't have any radioactive background coming from the material of the detector itself, okay? And this is absolutely critical. That's not the case for argon. Argon has a naturally occurring radioactive isotope that is argon-39. This decays and produces gamma and radiation in your detector, and it's extremely hard to separate argon-39 from the argon-40. That is what you want in your detector. So you are going to have an irreducible background that you have to deal with inside your sensor, okay? And that is a big problem for the argon detectors. There are ways of dealing with this. One of them is just looking for sources of argon that are coming from underground. We can discuss at any point why this element is produced, but for now, there are sources of argon that are cleaner that you can get. So you can go to some mines and take argon from them, and that argon has a lower percentage of argon-39 in it, so you can do better things. There are also efforts in trying to isotopically separate argon-39 from argon-40, but this is very, very, very hard, okay? And for neon, the thing is that it doesn't matter if there are radioactive isotopes. Well, there are no radioactive isotopes of neon. And the thing is that because the vapor pressure is so low, so you need to have around 20 Kelvin in order for the neon to be liquid, all the other impurities just freeze out. So it is very clean just by the thermodynamic properties. So this is the table. Argon turns out to be, the other thing here is the price, okay? And you will see that, this is important, especially if you are trying to build a ton scale detector, okay? So here the cost of the xenon is huge. So this gives you an idea when you are thinking about a ton scale detector that typically has tens of tons of xenon in itself. So it's 10,000 times 1,000 roughly. That's a lot.
Javier,
Okay. Yes.
is this the extraction cost or the total cost?
This is when you, just including purification, bottling, and everything. So when you go to the industry and say, okay, I want to buy xenon, they say, yeah, no problem. Yeah, $1,000, you have 1 kilo. Okay. I mean, this is a rough estimate. This is not the bulk cost, but it's ballpark. Okay. Oops. Yeah. Okay. So, so the other thing is that with this price tag, that is the biggest disadvantage of xenon other than the mass itself, that is a heavy nuclei, is that, well, experiments essentially look like banks, okay? You buy xenon, but then you have a stock that you can essentially sell. So there are experiments that actually have made money during the running of the experiment, because they buy the xenon at the beginning, and then the prices go up, and when they sell it, they actually have extra money after running. So that may be an advantage, actually, yeah. So now, going into the different techniques, the simplest one is what it's called the single phase detector, and that is just a volume filled with whatever noble liquid that you select, okay? And then you have light detectors all around. So in this design, this is the simplest thing that you can do. You are essentially just looking at the scintillation light that is produced in this volume. And if you have a good design, you are able to collect the vast majority of these photons, and also by looking at the intensity of the light that you receive in each of these photosensors, you are also able to kind of reconstruct the position inside this volume, which is, again, very important if you want to fiducialize and just select the areas that are at the core of your detector and that are cleaner, okay? In this design, there are many, many examples. I'm going to only show one example per technology, but there are many. We can discuss the details of the different efforts. This one here that looks like a Death Star, it's a 3-ton detector that it's running at Snowlab. It's called Deep 3600, okay? And all of these things are photomultiplier tubes that then are coupled into a ball that is at the center, that is this acrylic vessel, that it's filled with 3 tons of liquid argon, okay? There are experiments using xenon instead of argon. The biggest one right now, it's called Christmas or Xmas, okay? But there are efforts using different targets. In this case, I chose argon as the example for the single phase detector because of a very nice characteristic that is very much used as an advantage in argon versus xenon detectors, okay? Yep. Yes, it's just liquid, and it's a completely homogeneous detector.
Can you repeat the question? Just.
Oh, yeah. She asked why this is called a single phase detector, and the reason is that, yeah, all the target material there is in a single phase that is liquid. Okay. In principle, you could just run this as a gaseous detector and have just gas instead of liquid. And sometimes it's done during commissioning, but the total mass it's really low. Okay. Okay. So this, what I'm going to tell you, happens both in argon and in xenon too, but with a very critical difference. So what you have when you start, it's an atom for argon or xenon, okay? And then it gets excited by some ionization, in this case, I don't know, whatever, a proton, okay? But whatever, it gets some energy. And there are two things that can happen. So it can go into an excited state directly, or it can ionize, and then coupled with another argon nucleus that it's there after it is ionized, and produce like a argon molecule, okay? And then it captures an electron from the environment, and then it gets into this state that it's called a triplet. Again, these two things, or this other path in which the argon just goes to the excited state immediately, and it can also go into this triplet or a singlet state. In both situations, what happens, it's that you end up in a molecule in an argon molecule, but these two things are in a different excitation level. So they will last different amount of time until they just dissociate and produce light. They will produce essentially the same wavelength, okay, no difference there, but the lifetime of these two states is very, very different in the case of argon. So you can have 5 nanoseconds compared to 1.5 microseconds. So we are talking orders of magnitude difference here. In xenon, there is a difference, but it's not as big. It's only a 5-fold, okay? So we can explode this to identify nuclear recoils from electron recoils, because it turns out that nuclear recoils and electron recoils produce these two states in a different fraction, okay? So in nuclear recoils, you pretty much produce a lot of the fast-lived ones, okay, and very little of the other states that live longer. And in electron interactions, you produce a lot more of these other bounded molecules that live much, much, much longer, okay? So when you look at the signal, if you have a digitizer that is fast, in a nuclear recoil, you will just essentially see one big spike and very little after. And in an electron recoil, you will see the big spike, but then a lot of decaying grass after that. So you can use this to discriminate between a nuclear recoil and an electron recoil. And here is real data. This is from DEEP. Okay, and what you can see here is this band, that is the electron recoil band here, and in this section here are the events that are produced by nuclear recoils. Okay, so just by selecting in these two variables, you can essentially discriminate between nuclear recoils and electron recoils. And the discrimination in argon is amazing. At least it is amazing for relatively high energy. When you go to the lowest energy, as always, everything gets mushed up and you don't have any discrimination or very little discrimination. But at high energies, it looks amazing, and the discrimination is 10 to the 8th. So you don't confuse an electron recoil and a nuclear recoil event. Okay? So, but you can only do this kind of amazing discrimination with argon. You can still play this game with xenon, but because of the time scales are so much closer in xenon, these two bands are essentially very, very close to each other. And there is another technique that we will discuss later that is mostly used in xenon. Yes?
Could you repeat what are you showing in this plot? I don't understand the
Yes,
the plot.
sorry. So in this plot, the x-axis here essentially is the amount of photons that are seen after an interaction, okay? So you have a particle that comes into the volume of your detector, it deposits some energy, and that produces some light, and you detect that light. So this PE, it's photoelectrons, so this here is the number of photons that you are seeing after an interaction, okay? So each vertical line corresponds to exactly the same total amount of photons, okay? And in this axis, essentially what you have is the time scale of the signal, how wide it is, okay? So, or the inverse of that actually, because, yeah, sorry. But essentially it's a measurement of how wide the signal is. So if you have things that are electron-like, okay, in this y-axis, they will be around this value because all of the spikes look the same and they are just spikes with sorry. In this case, the thing is that, well, in this case, okay, what you would have is just a lot of grass if it's an electron event, okay? And if it is a nuclear recoil, you won't have any of this grass. So if you look at how is the spread in time for these kind of signals, it will be much longer than when you look at the spread in time for these signals. And in this plot, sorry, decided, I mean, this is normalized to 1, and they transform these 2 parameters of how time spread it is in something that goes from 0 to 1, and it's actually reversed, okay? So the ones here are the ones with the longer time, and the ones here are the ones with the shorter time, okay? Sorry, I didn't.
What about the color bar?
The color bar is the number of events that you have in each bin. So this is a 2-dimensional histogram. So the ones that have, for example, here, you have a lot of events compared to what you have here, that you have less events. Okay?
Okay, thank you.
This is, might be, this is the fraction of the signal, right?
Yes,
In a given time
exactly.
window.
It's a fraction of the signal. Yeah.
Yeah.
Yep.
Just to clarify, would WIMPs always cause nuclear recoils then?
Yes, I mean, at least, I mean, you need some kind of model to interpret your data. That's always the case, okay? The WIMPs, the cross-section is much, much larger for nuclear recoils than for electron recoils. So you would essentially assume that is completely dominated by that channel. That doesn't mean that WIMPs cannot interact with electrons, but it means that the vast majority of your signal is going to come from nuclear recoils. And in a discovery search, yeah, because you are very close to the minimum number of events, they will all be nuclear recoils. Okay?
Thank you.
Okay, so moving forward. So this was the kind of the last slide for the single phase design for detectors. There is another design that was pretty much, I mean, that has many advantages, and is the go-to technology for xenon detectors that essentially cannot really play this game for discriminating nuclear recoils and electron recoils, okay? So in this design, what you have is a vessel in which you have 2 phases. One phase that is the main phase, it's liquid, and then you have on the top a little bit of gas. The reason for doing this is that in addition to light sensors surrounding this volume, okay, you also have here, just above the surface of the liquid, a grid that has a very, very, very high electric potential. And that will produce that when you have charge that is very close to this grid, it will be extracted from the liquid and accelerated, and that in turn will produce a light signal. Okay, so this, and we will see how that is used by this idea. We also have now an electric field that goes in this direction. Okay, that is different from the single phase, in which the design was much, much, much simple. We didn't need to have any electric field or this super fine tuning between a grid and the liquid and other stuff. Okay, but let's say that we have an interaction here, a mu1, for example, that produces some interaction in the volume, and this thing here will produce some scintillation light. Okay, so this scintillation light, and also it will produce some amount of ionization in this position. So this scintillation light will travel very fast and be seen by your detectors. Okay, and in the bottom I'm just plotting the amount of signal seen by the overall, all the sensors that you have here, okay, against time. So you get this signal that it's called S1, that is very fast, and it happens almost immediately after you have an interaction, and this is scintillation light. But now you have this electric field, so all these electrons that you ionized after the interaction, they don't recombine in place. So in a single phase detector, they will just stay in the same location, recombine, and produce light later on, more light. So in a single phase detector, you actually produce more light than in this time projector or dual phase detector, because of this ionization effect that you separate and you don't let them recombine. So then, because you have this field, the electrons will start to travel to the surface, okay? And this takes a long time. You can see after your signal, they travel, but this is, they are traveling just by diffusion with this electric field. They don't travel at the speed of light, okay? So it takes a long time. But then when they get to the surface, they are extracted by this grid that, because it has very, very fine wires, it amplifies the signal. So I don't know if you've seen this in other neutrinos detectors, but what happens is that when you have an electric field in something that is extremely small, the electric field gets amplified in the proximity of this very pointy or sharp or small scale thingy, and there the field is so high that the electrons are accelerated and they collide with the other the other atoms that are in the gas there, and when they collide, this starts an avalanche, similar to what you have in a photomultiplier tube, that they multiply, 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 and they produce a lot of light. So you have here a flash of light that is actually much larger than the scintillation signal that you had there. It's like a spark, if you wish, okay? So you have then this huge signal here. And this is a very, very smart design, because having these two signals allow you to do many things. One thing is that just by looking at what's the time difference between these two signals, you can tell where this event took place, because you know what is the speed at which the electrons travel through the liquid, okay? And just by simple kinematics, you can reconstruct where it happened. So it gives you a very good spatial resolution in this vertical direction, okay? The other thing is that the size of these signals, okay, will depend on essentially how much ionization versus scintillation light was produced at the very beginning, okay? So, and this we know that it's different for nuclear recoils and electron recoils. So in xenon, even though these two states are very close in lifetime, the two states, that excited states for the xenon molecule, they are produced at very different rates depending on how much, if it's a nuclear recoil or an electron recoil, and they will produce different amount of ionizations that you are splitting at the very, very beginning of this. So you don't let this recombine, and looking at the fraction of this will allow you to have a very good separation between nuclear recoils and electron recoils. And this is the preferred technique for xenon. And we will discuss how good it is in a few slides.
I have a question.
Yes.
So do you need to have this dual phase to have the electric field?
Well, it's not just for the electric field. You need to have the avalanche, the multiplication, and for that you need a material there. And yeah, the simplest way of doing that is by having the same material as in the liquid phase, because all your optical sensors are tuned to this particular wavelength, so you want the same wavelength, and also, yeah, it's the simplest by far.
Thanks.
Okay. You don't have to worry about adding additional sources of contamination. In these experiments, you always want to minimize the amount of different elements or materials that you are using, because each of them you need to screen, clean, and stuff. In this case, it's a much simpler design. So I'm going to use xenon n-ton as the example for this technology. There are many other experiments that use dual phase TPCs. We can discuss them in the coffee break. But yeah, essentially the way most of these experiments are designed is pretty much the same. So I'm going to use this just as an example. So you start with a mountain or a lot of material, because you want to stop the cosmic radiation. The environment is, our environment is constantly bombarded by cosmic rays and radiation from outside, that the only way to stop it is to add a lot of material. The simplest way is a mountain, but you can also have these things in mines, like Snowlab. So the xenon enton detector is in Gran Sasso, that is in a mountain. It has 3 big holes, and xenon is located there. So you start with that. Then after that, you place your detector inside a big shield, and we are going to discuss this. And look at the scale of this thing. It's huge, okay? This is like a building size experiment. This here has 3 levels with offices and machines for purifying the xenon and keeping these things running. So this thing is huge, okay? Now, if we look at our detector from outside, we have this big tank that is the outside shield, and this has just a sign showing what's inside. This is printed there, okay? But if we look inside, after the mountain, to reduce the amount of cosmic radiation to a manageable level, we have another kind of layer, Russian doll, that is the muon Vito. That is this big water tank that is surrounding the core of the experiment where the sensor is located. So this is all filled with water, and you have here photomultiplier tubes that are looking at light, and when a muon goes through water, if it is a high energy muon, it will produce Cherenkov radiation. You already heard about this in the previous talk yesterday, okay? So that light will be seen by these 84 photomultiplier tubes that are looking in, and you will be able to tell whenever a muon goes through your system. And that is very important because muons can produce cascades and can give you other issues inside your sensor. So you use this to tag sometimes in which a muon came through, and then you beat all the data that was collected during this time window. So you have a much cleaner sample. After that, we are focusing on the inner part of this, and then there is another Russian doll layer, okay? Here you have the neutron Vito. Here it's a very similar design, okay? Inside this vessel is our TPC, but it is placed inside another volume that has gadolinium salted and water. And the reason you add this thing here, okay, is because this thing captures neutrons once they thermalize. So if you have a neutron event in your volume, it will look exactly the same as a WIMP event because it's a nuclear recoil, and you want to be able to tag those and discard them. So the way they do it is that, well, you have a neutron event, it produces a WIMP-like event inside your TPC, but then it goes outside. And outside it is captured by the gadolinium, and then it decays. And when it decays, it produces a lot of light. So essentially, you are seeing the light of these delayed neutrons, and you can also use this to veto the time windows that happened before. So you are using this as a delay veto to see whatever event you have in here, if it is a candidate for being a neutron or a WIMP-like. Yes?
So I imagine that you have like the gadolinium layer on both sides of your main detector volume, right?
Oh yeah, so this is in the center of this volume, and it's completely immersed in this liquid, yes.
So if the neutron didn't hit on the first time you went through it, like on its way towards the central volume,
Yes.
how can you make sure that it's going to hit on its way out?
So here, what you are looking for is not so much events that are coming from outside. Well, you have neutrons that are coming from outside and are seen by this, but the things that worries them, I mean, this is relatively big. So the neutrons that are traveling through this have a very high chance of being captured, I mean, thermalized and being captured in this large volume of water, okay? So going from outside without producing any interactions, it is possible, but it's very, very, very unlikely, okay? And the thing is that it needs to get in here with enough energy to produce a nuclear recoil that you can see, because also the TPCs has an energy threshold, and if the nuclear recoil is below this energy threshold, you will not see it, okay? You will discard it. And if it has enough energy to produce that, it definitely has enough energy to come outside, or not definitely, but very likely has enough energy to come outside. So you are using this mostly as a delayed tag, not so much as a pre-tag, okay? Although you can also do that. But the thing is that in this case, you are able to see neutrons that have a very, very low energy, much lower than you would be able to see inside here, okay? And you are using that to tag whatever events you happen to have inside the vessel, okay?
Thank you.
Yep.
I am a little bit confused because in the previous slide we started with muon coming from outside, right?
Here?
In the previous,
Yes.
we started with a muon, and then we are talking about a neutron.
Yes, so I mean, all these different layers are designed to handle different types of radiation. Okay, the outside layer, this big water tank, is designed to handle cosmic radiation, in particular cosmic muons. Okay, the inner part is designed to deal with a different kind of background. Okay, the neutrons here are mostly coming from radioactive materials in the surrounding of our detector, okay? So there you can have neutrons that are produced and they travel towards your detector and you are trying to veto those. These are not cosmic neutrons, but radiation that is produced inside your detector, okay?
Thank you.
Okay, so so this is the neutron veto that is an active veto in the same sense that the outside water tank is an active veto for shielding muons. Both of these are built with extremely radio pure materials, so they are also a passive veto. So if you have radiation coming from outside, it will most likely be stopped by these two things also, in addition to the active vetoing. So now we finally get to the TPC, okay, that it's at the core of all this, and this is how it looks like. So you have a vessel that it needs to be a pressure vessel able to withstand having all this liquid material there that wants to be a gas, okay, so it needs to be a high pressure vessel, and inside of this, submerged, you have here photomultiplier tubes that are on the top. Here you will create this gas pocket, okay, between the liquid and the tubes here. About this height, you have this grid, okay, that extracts the electrons and produce the second flash. And up to here, all of this will be filled with xenon. So here you have the bottom layer of PMTs, and all of this is kind of submerged in xenon. Okay, so that was a drawing. This is how it looks like. So it really looks amazing. These are all the photomultiplier tubes that are looking into the xenon volume. This is how it looks when it's closed. And all of this, it's done in a ultra clean room, okay, like we discussed yesterday. So these detectors are large, they have large volumes, so they really need to worry about radioactive contamination and radioactive background. So all of this handling, construction, cleaning, everything is done in ultra clean environments, but people raise like this. After you do this, you put everything inside your detector at the core of the two other detectors that are vetoing outside or inside radiation, and then you run. So just to go back and summarize quickly the idea of the dual phase TPC. So we have two volumes, gas, liquid. An event that happens, it produces scintillation light and ionization. You will be able to see both this immediately and this delayed. So by the time of the drift of the electrons towards the surface where they produce the second flash, then you can reconstruct the position here, and by looking at which photomultiplier tubes have seen the first flash, then you also can reconstruct the other coordinate here, okay? So you have 3D reconstruction, and you have the ability to separate between nuclear recoils and electron recoils by looking at the size of these second signals compared to the size of the first signal, okay? So this is your tool set. And how does this discrimination between nuclear recoils and electron recoils look like? So here is calibration data from xenon. This was taken by xenon 10. Now we have a much larger detector, but essentially is the same, okay? And what you have here is this distribution are events that are produced by nuclear recoils. And in the X scale here, you just have a variable that is a function of the ratio between the second signal and the first signal, okay? So here, if the second signal is large, you have the larger second. Yes, I'm always confusing. Yes. So here you have the largest second signal, and here you have the largest. Sorry, all the other way around. Here you have the smallest second signal compared to the first one, okay? And here you have the largest second signal compared to the first one. And although you don't get as an amazing discrimination as in the case of liquid argon, you do get pretty good discrimination. So here, for xenon 10, the rejection is 99% if you take an efficiency for the nuclear recoils of 50%. And what does this mean? So it means that if you set a cut here, okay, at about half of the distribution, or where the peak of your distribution of nuclear recoils are, and you say, I'm going to throw away all the events that have a ratio between the two, S1 and S2, that is higher than that, so I'm going to throw away half of my nuclear recoils events, okay? Then the remaining half of the events will be much, much, much cleaner. And I will be able to reject 99% of the electron recoil events, okay? And this is something that is very common in dark matter experiments, that you are willing to reduce your efficiency and throw away a large fraction of your events just to get a cleaner sample, okay? Okay, so this is how it looks in 2D. So here we have the first signal and the second signal, and on the top, then the ones with the larger second signal, we have the electron recoil, and then here the nuclear recoil events. So by having a region here in which you reject all the things that have a large second signal, you are able to keep roughly 50% of your efficiency, but it is a very clean sample, okay? This is also real data. This is coming from xenon n-ton, so the current iteration of the effort, the largest one, with many tons of liquid xenon inside. Okay, so after you run like this, okay, when they do, I mean, this is calibration data, so you have a lot of stuff here, but when they actually do run, they don't see any events in the region that they have selected for the nuclear recoils, and then they proceed to place a limit. So here, this line is the limit, the latest limit produced by xenon n-ton. So what are these plots? I know that you've seen it a lot before, but from Dario, I've heard that it would be good to discuss this a little bit with a little bit more detail. So this is essentially a plot in which the x-axis is just the mass of the candidate. So the further you go in this direction, the heavier the dark matter candidate you assume it is, okay? And remember, you have less events, so less particles that can scatter with your detector if they are more massive. And in this axis, the y-axis, is the cross-section, essentially. What is the probability of seeing it in the interacting with standard model particles? Okay, so what these lines mean is that, for example, if you have an event, a cross-section here that is 10 to the minus 43 and a WIMP mass of 10 MeV, you would see a rate that would be so high in your detector that you would have seen a lot of events in your detector. But if you don't see any, then you say, okay, I start lowering the cross-section until I get to a position in which I don't predict to see any in my detector, essentially. I mean, and that is this line. So what this line means is that whatever it's above it, it's rejected, because if nature was like any of the points here, you would have seen it in your detector, okay? Then moving forward. So that was the xenon n-ton result. That is not actually the best result that we currently have from TPCs, from xenon TPCs. This is just a history of what's the best cross-section for a given mass of 50 GeV, so it would be something around here, okay? What is that cross-section for different experiments? And the better the experiment, the more sensitivity is, and the lower you are able to go. Okay, so the current record it's by LC, that is also an experiment using a xenon TPC, and that is the design is pretty much the same as what I discussed before. And then the red squares here are the planned experiments for the future. All of the xenon experiments are going into a grand unification. They are all merging into one single effort to accumulate, I think it is about 1/3 of the total xenon mass available commercially in the world, which is a lot, okay, to get here. But this has not happened yet, so we are here. So this is the best result. This is the result coming from LC, okay? That is better than the result coming from xenon n-ton, that is around here. And what you have at the bottom is what we call the neutrino floor or the neutrino fog, that this essentially in the past has been seen as kind of a hard wall that it will be very difficult to improve on. These are the events that you will start having from environmental neutrinos interacting with your detector, okay? So you've heard that neutrinos can also produce interactions that pretty much mimic the ones of a WIMP or a neutron, so they will produce nuclear recoils in your detectors, and you have a flux of neutrinos that are coming from different sources. I will discuss in a little bit which sources, that will ultimately provide an unreducible background to your experiments. So once you get there, it's not a wall, because you can still keep making your detectors bigger, but it's going to be harder, because you will need to understand this background with a precision that needs to be good enough so you can subtract it and keep going. So that is not easy, because you really need to understand this background very, very precisely in order to do that. But in LHC experiments, it's done continuously. Okay, so when they are doing whatever search, they are flooded by events, and they subtract this by modeling the background and subtracting it. Okay, so the other thing is that this is the way it is typically presented, this neutrino floor, but not all the neutrino floors are born equal. So when you see these together in a plot that shows experiments that use different targets, it's actually not correct, because here in this axis, you have selected a variable that is a transformation of what you see after taking into account the material of your detector, the target material of your detector. This is translated into dark matter and nucleon cross-section, but the coherent cross-section from a neutrino will be different depending on the target. So here, what you have is a very nice paper produced by Xenon, in which they plot the different neutrino floors that you expect for different experiments using different target materials. And for example, if you are using lighter things, then you expect things that are, for example, helium, you expect things that are very, very different from the neutrino floor that you expect from xenon. Okay, so when you see these plots, you always need to be aware that you need to compute your neutrino floor for the particular material of your experiment. Okay. Then let's dig a little bit also in this neutrino floor. So there are many different sources for the neutrinos that are coming. That are coming into your detector. And in here, so again, in this plot, we have the WIMP mass on the x-axis and the cross-section with the nucleon on the y-axis. And the colors here reflect what's the intensity of these fluxes that you expect. What is the number of events that you expect to see from these different sources? So you have the atmospheric neutrinos, okay, but you also have reactor geoneutrinos that are coming from the environment, and all of these things will produce hotspots in which you expect to see a lot of events on, okay? But these orange regions are regions in which you will have some events already spilling from these sources. And the easiest one to see, or the one that we are closer, is this one, beryllium-8 neutrinos that are coming from the sun. And actually there is, I mean, these neutrinos have already been seen by dedicated experiments looking for this. And you've heard about this in the previous lecture. So, the other thing is that now there is a claim by Xenon that they have also seen it in their detector. Okay, so there is this. I'm not going to go into details. This was presented in IDM conference last week, but essentially what they see is that they observe an excess over the no signal hypothesis that is about 2.7 sigma. So this is not yet discovery in the sense of the 5 sigma rule, but they are starting to see a signal there. And probably LC or other experiments will definitely see this, or even xenon Anton with longer run. So I'm out of time, so I'm going to stop here. And yeah, if any questions.
More questions to Javier? Over there.
Hello. So, in light-dark matter scattering with electron search, we usually use only S2 for dual-phase detectors. Could we also like try to search for this light-dark matter scattering with electrons in single-phase experiments?
So, I mean, it depends on the backgrounds of your experiment in your single phase. So let me comment a little bit on the question. So I didn't have time to go into a lot of detail on the light dark matter searches. So all of these slides have been focusing on the WIMP-like searches that are above 1 GeV for the dark matter mass. If you want to go to lower masses, you can do that by looking at dimmer signals that would come from interactions that produce a lot less photoelectrons there. And also, when that happens, essentially, the first signal, the scintillation signal, that is the smallest one, you remember, is this one, this signal at the beginning. If you have an event that is very low energy, you will not see it, okay, over the noise. You will only see the S2 signal. So when you want to go to lower energies, you have to rely on the S2 signal only. That is much, much larger than this because it has amplification when it gets to the surface, the ionization. In dual phase TPCs, there are many analyses that are done for this low energy region, looking for light dark matter candidates using S2 only signals. These are typically not background free searches, so you have some background there and you are trying to see other stuff, like for example modulation or other characteristics of the events that you see. But then there, of course, you don't have any nuclear recoil, electron recoil discrimination, and also you don't have information about the C coordinate here because you don't have this drift time. You only see the second kind of flash here. Okay, and the question was, okay, this is done for dual phase TPCs. Can you do this in single phase TPCs? And the answer is yes, but the threshold is much, much higher. Because although in single phase TPCs, the scintillation light for the first flash is bigger, it's still smaller than what you get for the second flash in here, okay? So essentially, you can do it, and people are doing this, but it's the sensitivity, it's usually, it's harder to get there.
Here, another question. Here. Okay.
There?
Yes. So usually when you talk about this neutrino fog and how to beat it, the main focus is always on directionality. But are there any other detection strategies that could maybe improve the situation to get through this previously irreducible background of neutrinos?
Not that I am aware of. So the directionality is one strategy that you can have here. So the thing is that, well, if you are looking at, if you have a detector that is able to tell you the direction in which the dark matter is coming from, then, for example, you could look in a direction where you don't have these neutrinos, or that the neutrinos that are coming from the sun, for example, well, they are coming from the sun. Okay, so if you see an event of something that is coming from a different direction, then you would be able to tell that this is not a neutrino and it's likely a dark matter event. So directionality, has been the go-to technique to go into this fog. The other thing is what I mentioned before, essentially be able to do very detailed modeling of this and have different technologies, because if you have different target materials, you will be able to say something, because the rates as seen here, okay, for the different target materials will be different for neutrinos. So you should be able to also to tell a lot about your signal if you see it with different target materials. And that is something that is, I think, general for dark matter. I don't think anybody will believe that, well, I don't think that the community will believe that we have seen dark matter without any doubt with just one signal. The same as with DAMA, even if it's an experiment that it's super open and everybody is super happy about this experiment, with just one signal, I don't think that will have the convincing power. But once you have one signal, you know where you want to put your effort, and then you start designing other experiments with different target materials, different techniques, to try to cross-check that signal and get more information also, and see if it's compatible with neutrinos, with other sources of background. Just one signal won't be enough.
Thank
Okay.
you.
Okay, so I suggest that we break that we stop for coffee break now, and then remember that there is this half an hour question session later. So if you have more questions, just save it for later. And so Martin has some announcements. So we should just thank the speakers again in the morning.
Thank you.